Next, sum number 2 says, show that the relation R defined on a set A of real number. A is the set of real number. It is defined as R is a set of ordered pair AB such that A is less than equal to B square. The first component is less than equal to square of the second component. First component is less than equal to the square of the second component. If any ordered pair satisfying these conditions will be the part of this relations. What we have to do is we have to prove that this particular relations defined on the set of real numbers is neither reflexive nor symmetric nor transitive. Now what to do, how to do? Now to prove that it is neither reflexive nor symmetric nor transitive, what we'll do is instead of giving a general proof for this, we'll try to find out an example of an ordered pair which will violate the reflexive nature, or another examples, or maybe the same example will work, which will violate the symmetric nature and the transitive nature of this relation. So rather here, instead of giving a general proof, we'll look for an ordered pair, a particular ordered pair which will violate this reflexive, symmetric and the transitive nature. Correct? Now to disprove that it is reflexive, I need to look for a real number x such that xx is not a part of this particular relation. Now you can make some observation here. If x is greater than 1 or 2, 3, 4, like 2 will always be less than 4, 3 will always be less than 9. So these all numbers are the part of this relation. But if I take my number between 0 and 1, say if I take my number as half, then half will not be related to half because half will not be less than half. What is the square of half? Square of half is 1 by 4, and we know half is not less than equals to 1 by 4. In fact, half is greater than 1 by 4. So if I take this half belongs to the A, the set of real numbers, A is the set of real numbers, then this half is not a part of the relation R. Will not belongs to the relation R because this half is not less than 1 by 4. So this particular ordered pair disprove the reflexive nature of this particular relation, meaning this relation is not reflexive because there exists an ordered pair half-half, there exists an element half belongs to it such that half is not related to half, means half is not a part of this relation, so it is not reflexive, right? If you recall, what was the reflexive nature? For all x belongs to A, xx must belongs to R. Now there is an x belongs to A such that xx is not belonging to R, so this particular relation is not reflexive. Correct? Now for symmetric, if you recall, what was symmetric? If AB belongs to R, then BA must be a part of the same relation. Clearly, can I write 1 and 3 belongs to R? Because 1 is less than 3 square, correct? But can I write 3, 1 belongs to R? 3, 1 will not be belonging to R because 3 is not less than 1 square, 1. So 3, 1. For 1, 3 belonging to R, 3, 1 will not belongs to R, meaning there is an ordered pair, say 1, 3, AB belonging to R, BA not belonging to R, then the relation is not symmetric. This is not symmetric. R is not symmetric. This particular examples 1, 3 disprove the symmetric nature of this particular relation. Next, transitive. To prove that it is not transitive also. It's easy. There are many examples. I'm not saying this is the only example, this is the only example. There are many examples. But one example is enough to disprove a particular nature of this particular relation. I don't need more than one example. Just supply one example that will disprove the reflexive nature, or that will disprove the symmetric nature and the transitive nature of this relation. Right? Clearly, if I write, can I write like this? Belongs to R, because 100 is less than 11 square, which is 121. So 100 comma 11 belongs to R. Correct? 11 and 4 also belongs to R, because 11 is also less than 16, 4 square. But AB belongs to R, BC belongs to R. Can I write AC belongs to R? 100 is not less than 4 square, 100 is not less than 16. So means 100 comma 4 will not belongs to R. Will not belongs to R. Meaning this particular set of ordered pair, 100 11 belonging to R, 11 4 belonging to R, this will not, from this two I cannot write 100 and 4 belonging to R. Means the relation R is not even transitive. So it is not reflexive, not symmetric, and not transitive.